Okay, I'm live, allegedly. See, we got sound and video. At least half of those. Okay, so has everybody figured out the registration thing? That should all be taken care of at this point. Okay, so this week we're going to start with probability with continuous random variables. And this is probably most difficult week. We're still working on the first problem set with discrete random variable and a lot of conditional distributions. So that is to sort of set the stage for what we're going to do this week. But people still working through that have had some good discussions, campus wire and office hours, and hopefully continue on that. Everybody can get through it pretty well, but we're going to start learning about continuous random variables, at the same time, Tuesday, Thursday, which are harder than discrete random variables to deal with. But once we get through that, it gets a little bit easier for a little while. So before we can talk about continuous random variables, I have to talk about the fact that I'm subject to the conflict of interest policy due to developing Stan at Columbia and also using Stan outside of Columbia. We haven't really talked about Stan that much yet, but you should go ahead and install it for Thursday. Actually, installing the RStan package is not particularly difficult, but that's not sufficient to get it to work. You also have to have a C++ tool chain, which unfortunately is different from Mac than it is for Windows, and it's different from Mac Catalina than it is from older Mac and things like that. So that is a little bit involved. We have a wiki page that has instructions that should take care of things, but if you want to stay after today, I don't think the next class gets here till 6. We can do it together. Or if you have questions, we can make a thread on CampusWire, which you should all definitely at this point be on, asking questions, answering questions, etc. So we talked the last couple of weeks about these things called probability mass functions over a discrete sample space omega. It could depend on some parameters generically called theta. That tells us the probability that you knock down 4 pins out of 10, exactly 4 pins out of 10 in the first roll of a frame of bowling. In contrast, the so-called cumulative mass function, or CMF, is defined as the probability that some discrete random variable, capital X, takes on a value that is less than or equal to a given value X, conditional on the parameters. And because the events in the sample space are mutually exclusive, it's just probability that it's X, or it's 1 less than X, or it's 2 less than X. You just sum those up to get the so-called cumulative probability that a discrete random variable is less than or equal to little x. And in the more simplified model for bowling that's just based on ratios of Fibonacci numbers, no parameters, we can actually write this cumulative mass function in a simplified form. Probability of knocking down less than or equal to little x pins can be written as -1 plus the x plus 2 Fibonacci number in the numerator divided by -1 plus the n plus 2 Fibonacci number in the denominator, and that is equivalent to this summation on the previous line, which is true in general, but with the magic of Fibonacci numbers, we can write that really concisely for this case. So if you source in this URL, which has the code from the first week to define the Fibonacci function and also the omega sample space, we can then define the cumulative mass function as a function of x with a default value of n equal 10 pins. That is just the ratio of those things. And then if we evaluate that cumulative mass function over the entire sample space, we get these numbers here, which are between 0 and 1. And we want to know, well, how do we know that this cumulative mass function that we have defined here corresponds to the probability of getting exactly little x pins. There's some seats in the back there, and also one there. Exactly x pins out of n, which was this other function that we defined starting on the first Thursday. So if we look at the 0 here, so this is allegedly the probability of getting less than or equal to 0 pins on your first roll of a frame of bowling. But less than or equal to 0 is equivalent to 0 because you can't knock down negative pins no matter how bad you are at bowling. So this should be equal, this should simplify to the probability you get exactly 0 pins. And then we can see over here that, okay, if we evaluate this at 0, that's the second Fibonacci number starting from 0. So that's 2. 2 minus 1 is 1. And so we get 1 over what we had in the denominator before, which is the same as evaluating the Fibonacci number at 0, which is 1. So this first one, that makes sense. Then obviously 10, the probability of getting less than or equal to 10 pins on the first roll of a frame of bowling, that has to be 1. So that makes sense, right? Okay. So what about, for the ones in the middle, like 9? So here we're saying the probability that you get less than or equal to 9 pins on the first roll of a frame of bowling is 0.616. How would we know or be able to check whether that is consistent with our probability mass function for knocking down exactly 9 pins? Okay, yeah, we can do it the hard way. Summing up, that would be 9 numbers, which is a little bit hard to do in your head.
We can do it for 10 and then subtract it by 1.
We could do it for 10 and then subtract 1. So the difference between the probability that you knock down less than or equal to 10 pins minus the probability that you knock down less than or equal to 9 pins should be equal to the probability that you knock down exactly 9 pins, right? Or 10. Wait, I'm off by 1. Probability you knock down exactly 10, take 3. That's why you get 3 rolls in a frame of bowling. Probability you knock down less than or equal to 10 pins minus the probability that you knock down 9 or fewer pins should be exactly equal to the probability that you knock down exactly 10 pins. And so that would be 1 minus 0.616, which is this 0.384 number that we had before for the probability of a strike. And we could figure that out somewhat rigorously, insofar as we do anything rigorously in this course, by saying, okay, what is the probability x is less than or equal to 10 minus the probability x is less than or equal to 9. And so that would be equal to -1 plus the Fibonacci number, the 12th Fibonacci number starting from 0, minus -1 plus the 11th Fibonacci number divided by -1 plus the 12th Fibonacci number, right? Okay, so it has the same denominator there. So these -1s are going to cancel out, and we're left with the 12th Fibonacci number minus the 11th Fibonacci number. But what is sort of the definition of the 12th Fibonacci number? Right, it's the sum of the previous two. So this we can write down as Fibonacci of 11 plus Fibonacci of 10 minus Fibonacci of 11 divided by -1 plus Fibonacci of 12 in the denominator. So now our Fibonacci's of 11 cancel, and we're left with Fibonacci of 10, which would correspond to the probability of getting exactly 10 or a strike in your first roll of a frame of bowling. And that's the same function that we started with on the second day, and we have in the bottom here. So really, we've shown pretty much that this is true not just 10 minus 9, but the difference between any x and x minus 1 would be the probability of getting exactly x by taking the difference of the cumulative mass function, and then that should be the same as the probability mass function. Questions about that? I know I wrote it a little bit too low. Everybody can see? Questions?
Why the 12 and 11 there?
So 12 in the cumulative mass function, so -1 plus Fibonacci of x plus 2. So we're evaluating this at 10 and at 9, so 2 more is 12 and 11. But it would be true for any x, really. Good? All right. So another way of saying that same thing, what's the relationship between the PMF, the probability mass function, and the CMF, the cumulative mass function, is if we have number of pins on the horizontal axis here, and we have cumulative probability on the vertical axis here, the probability of knocking down at most x pins, and we have these bars that represent the cumulative probability, and we connect the top of the bars with line segments, then the slope of the line segments connecting adjacent bars is the value of the PMF. So we just showed that the difference, the first difference in the CMF gives us the probability. All these bars are one apart from each other. And so if you compute the rise over the run, but the run is just 1, then the slope of the lines connecting the top of the bars is the probability mass function. The rate of change in the cumulative mass function is the probability mass function. So the slopes of these line segments are equal to the probability of knocking down exactly whatever pins for the right bar that the lines connect to. So that is a very important concept, and that is what allows us to connect what we're going to do next to continuous random variables. So does everybody understand this point, that the rate of change in the cumulative mass function is the probability mass function? Okay? Let's try it with continuous. So now our sample space omega is going to be some interval, like all real numbers, all positive real numbers, bounded interval between two constants a and b, something like that. So if omega is an interval consists of an infinite number of points, each of which have a width of 0. And so we get into this thing that always seems a little bit paradoxical, like how do an infinite number of points, each with width 0, actually like take up space. But you have to do some sort of limiting thing here where you're allowing the probability of a continuous random variable big X being exactly equal to any little x. You have to let that approach 0. And so it's not particularly meaningful to talk about the probability that a continuous random variable is exactly equal to anything in particular. But what is well defined and very intuitive is the cumulative density function of a continuous random variable. That is the probability a continuous random variable big X is less than or equal to any x from your sample space omega. That could be a very well defined function, because the probability less than or equal to like 4.2 is something that is measurable. So the cumulative density function, or CDF, is a function from the continuous sample space omega to the 0, 1 interval. And that can be either closed or open, depending on the situation. So there's no real conceptual difference between a cumulative mass function and a cumulative density function. It's just the m and the d, they give additional emphasis as to whether we're talking about a discrete sample space in the case of a cumulative mass function like bowling, or a cumulative density function corresponding to a continuous sample space omega, which is what we're going to talk about the rest of the day. So I'll use capital F of some random variable, possibly conditional on parameters, to be both the cumulative mass function or the cumulative density function, because there's no real important difference, and it should be obvious from the context whether I'm talking about discrete random variable or continuous random variable. So the cumulative is the important part. This is a function that tells me less than or equal to little x. And I'll use capital F for that, and I won't use capital F for anything else except Fibonacci numbers. And even with the Fibonacci numbers, I use this like funny looking F. Yeah. Okay, so here is a cumulative density function from the sample space between 0 and 1. So that we have on the horizontal axis here. We have the cumulative density on the vertical axis here. We see we have a smooth curve rather than distinct bars, because we're talking about a cumulative space. And this curve here is defined as x plus the natural logarithm of 1 minus x multiplied by 1 minus x. And that is defined on the 0 to 1 interval. This is not a particularly useful CDF, but it doesn't have any parameters. So we'll start with that one because it's relatively simple. Okay, but the main idea is to think of, for these continuous random variables, what function can I use for the cumulative density function, the CDF, and then go from there. So one of the places that we usually do go from there, from the CDF, cumulative density function, is to the probability density function, or PDF. So the curve on the previous slide was that function there, which I've rewritten as f of x at the top of this slide. So just like in the discrete case, we can say what's the probability that x is greater than a, but less than or equal to little x, by taking the difference in the cumulative function. So evaluate the cumulative density function at x, subtract off the cumulative density function evaluated at a, and that gives us the probability that x, the random variable capital X, is between x and a, including little x but excluding a. So the probability of being between x and a is given by the difference, just like in the discrete case. Although in the continuous case, we can extend this. A does not have to be equal to x minus 1. A can be any number that is less than x, but still in the sample space. So if we make the particular choice that x is equal to a plus h, and we take the rise in the numerator and divide by the run in the denominator, so x plus h, or a plus h minus a would be what we have in the denominator. So when you subtract off a, you're left with h in the denominator, and in the numerator you have f evaluated at a plus h minus f evaluated at a. So that would be the slope of a line segment connecting x, or connecting a and a plus h along the horizontal axis, and their respective values of the cumulative density function on the vertical axis. That would be a straight line connecting 2 points, so a line segment. And for those of you who remember calculus, you can probably see where this is going. If we let h get small from above, then we have the definition of a partial derivative of the cumulative density function capital F. And that I'm going to define as little f of x. It's still the rate of change in the cumulative density function evaluated at x. And that partial derivative of the cumulative density function with respect to little x is known as the probability density function, PDF. That's going to be always positive because the cumulative density function is always increasing. But the point which you basically just have to memorize is the rate of change in the cumulative density function at x is a function, and that function is the probability density function, or PDF. And that's why I was emphasizing the connection between what we had in the discrete case, where the relationship between the cumulative mass function and the probability mass function is the line segments connecting the top of the bars, the slopes of those, the bars are the cumulative mass function, the slopes of the lines connecting the top of the bars is equal to the probability mass function. So the probability mass function in this way of looking at it is a slope. And that does generalize to the case of a continuous random variable, in which case we can define the cumulative density function, and the slope of the cumulative density function at a point is still the rate of change in the cumulative density function, and it has a special name, the probability density function, or PDF. And we can obtain the PDF from the CDF by differentiating it with respect to little x. Questions about that? Yes?
So, thank you. What I get confused about is that in like the previous week or maybe even before, in the textbooks, we have probability distribution function, and we say, oh, that's the same as probability mass function. Now we have probability density function, and I get confused as to like when to use which one.
Yeah.
No.
It doesn't help if you're a native English speaker because the words are too overlapping. So let me all right. Anything with cumulative in it this is the probability less than or equal to little x. And it doesn't much matter whether we're talking about continuous sample space or discrete sample space. Cumulative is the same thing, probability less than or equal, okay? Now, because there's not that much of a conceptual difference between those two, people often will be sloppy and use CDF for both of those. So you'll hear that. But that's kind of okay because there's not much difference between them anyway. Now, you will also hear some like older people will refer to the cumulative density function as the distribution function, which never seemed to clarify things for me at all. So I will not use the term distribution function, but if you encounter it in some older book or whatever, that's should be what they're talking about. Okay. Now, the distinction between probability mass function in the discrete case and probability density function in the continuous case has a little bit more meat to it. So the probability mass function is a probability. It's going to be a positive number between 0 and 1. The probability density function, PDF, in the continuous case is not a probability. It's the slope of a function that told us the cumulative probability. So the difference between PMF and PDF is important enough to remember if you can remember what the difference between M and D is. Mass is actual probability. Probability density function is kind of a weird phrase that somewhat makes sense in physics, but honestly, if you just think of it as the slope of the CDF, you're less likely to get confused. Now, furthermore, the videos by Ben Lambert, which I think are otherwise pretty good, refers to both probability density function and probability mass function as probability functions, which is kind of a shortcut for a phrase that covers both probability mass functions and probability density functions when there's actually some like distinctions there. But in a lot of cases, what we're talking about, the distinction doesn't matter so much, because the probability density function, although it's not a probability, is used in all the same ways that a probability mass function is used in the discrete case. So I don't know if that clarifies things, but there's multiple terms that sometimes are sort of used interchangeably, but I will try to be as explicit as possible what I'm talking about. And I'm talking about continuous things today, so PDF, CDF. So what then is the slope of the CDF at the top of the page at x? What do you got?
Can you repeat the question?
What is the slope of f of x? If capital F of x is that function there?
So we know this positive.
We do know it's positive. We know more than
And
that,
it's just
really.
the derivative of this.
Yeah, exactly.
Which is, help me out here.
1 plus 1 over x minus chain rule. So the derivative of ln 1 minus x times 1 minus x, which is 1 over 1 minus x. 1 minus
Q
x
minus
is 1.
log of 1 minus x.
Okay. Derivative of x with respect to x is, derivative of a sum is sum of the derivatives. Okay. So then in the second term we have a product. So what's the derivative, what's the general rule for the derivative of a product of functions involving x?
Derivative is one of them and the original one and how to say that in English?
F dash G.
Derivative of the first term times the second term plus derivative of the second term times the first term.
All right. So we have the derivative of the first term times the second term there. So what's the derivative of log of 1 minus x?
1 minus x. 1 over 1 minus x.
All right, and then we have a chain rule thing. So we're going to have 1 minus x in the numerator, 1 minus x in the denominator, and those are going to cancel. Okay, then we have plus the other piece, log,
Minus 1.
right. So log 1 minus x times times minus 1. So I'll just write this as the minus. So we have 1 minus, that's 1, and we're left with the PDF is negative log of 1 minus x in this case. All right. Now, we're not going to spend all our time taking derivatives. Most of y'all could do it in a pinch. Otherwise, you can ask a computer or whatever. So we'll do a couple of these just to solidify the intuition that the slope of the CDF is a function that can be evaluated at any x in the sample space, and that function is the PDF, and that function can be obtained by partially differentiating the CDF with respect to x. But you don't really have to memorize all the rules that you learned before. So anyway, we have this positive function that we can evaluate. So if we plot it, we have the black line, which is the CDF from before. Then if we plot the PDF in red, that's this curve. And so you can immediately see, in this case, the PDF goes above 1 because it is a slope, not a probability, despite the fact that the first word in PDF is probability, which is a little bit confusing, but we can use the curve function to get a quick visualization of any of these functions. And you can also see, although it's not super obvious from the CDF at the resolution that we have here, but the PDF actually goes to infinity as x approaches 1 because you get log of 0 multiplied by negative. So negative infinity times negative 1, positive infinity. Which is to say the CDF gets vertical right as it gets very close to 1. That's okay too. So PDF is not a probability, it's a slope, and slopes are allowed to be infinite. Questions?
Just what's it good for?
Oh, not much. Not this one. This is good because it didn't have any parameters to confuse you. But like the original bowling function we did, yeah, there might be some process that you think is well described by this cumulative density. I just certainly can't think of one. This doesn't have a name or anything. So if it were at all useful, somebody would have named it after themselves already. But that hasn't, and I'm not going to. So, whatever. Okay. Next thing we want to talk about before we get into standard normal distribution is the idea of an elementary function. Elementary functions, you can click on the link to Wikipedia. It includes the functions that you learned about, in high school. So just the addition, subtraction, multiplication, division, polynomials, rational functions, so ratios of integers, trigonometry functions like sine and cosine, the exponential function, e to the whatever, or any other, raising a base to a power you can handle, plus the inverses of all those functions and the compositions of all those functions with each other. So the elementary functions are closed under composition. If you sort of add or do some other operation of one elementary function with another elementary function, you get an elementary function. And these are basically the sorts of functions that we can evaluate explicitly, even though on a computer they might be evaluated with some other thing like Taylor series or something like that. So the PDF of the standard normal distribution, which can be evaluated by the dnorm function in R, all these PDFs and also the PMFs that are implemented in R start with D for density, and then they have some suffix that pertains to the name of the distribution. So the PDF of the standard normal is the elementary function. You have the part that depends on x, e to the negative 1/2 times x squared in the exponent there, and then is divided by the square root of 2 pi in the denominator. So that is clearly going to be a positive function. So that's good. And the standard normal distribution is so fundamental that it has its own Greek letter for its symbol, which is good. Okay, so that's the slope of some CDF. But what CDF is that? Well, the CDF of the standard normal, which you can evaluate by calling pnorm in R, is not an elementary function. So because the PDF is the partial derivative of the CDF, we can think of the CDF as being the definite integral of the PDF. That should be x there for the upper limit. So evaluating it up to x. But in any event, there's no explicit form for the integral of the standard normal PDF. So we just give it a different Greek letter to symbolize that integral. And that Greek letter is? Yeah.
Capital Phi.
Capital Phi. Got to learn the Greek letters. That's the easiest aspect of this class. All right. So just like in like American letters or whatever, we have little f and big F. to correspond to the PDF and the CDF respectively. When talking about the standard normal distribution, we use the lowercase phi to refer to the PDF and the uppercase phi to refer to the CDF. But the CDF is not an elementary function in the case of the standard normal. And there's a extraordinarily complicated algorithm known as the Risch algorithm. It took like 50 years for them to go from the paper version that was published of the Risch algorithm to actually be fully implemented in software. And you can't do it in R. But anyway, it is a more or less constructive algorithm that tells us whether some function has an elementary antiderivative, like you can do the integral in closed form. If so, it tells us what it is, but most CDFs are not elementary. So we just say, here's a Greek letter, and it represents an integral. But even though they can't be evaluated explicitly, in many cases, particularly in cases of integrals involving one variable, we can evaluate them numerically. So we don't really need the antiderivative. We just need the definite integral, the amount of area under the curve. And that can usually be done pretty well with little trapezoids that you add up. And the computer has more sophisticated things for that. So we can usually, with high amount of accuracy, figure out how much area is under the curve. But we can't necessarily write out an explicit form like we could in this case. We have an elementary capital F, and the derivative of an elementary function is an elementary function. However, the integral of an elementary function is rarely an elementary function. And so we just basically give it a Greek letter and say, okay, we'll put some algorithm in the computer to come up with the area, but we can't sort of give it an explicit form. That's usually the case with CDFs, and that's why it would kind of make more sense if we started with the CDF and differentiated to get to the PDF. So that's the way I like to think about it. But in practice, we're usually starting with the PDF, which is some positive function, and then trying to figure out what its integral would be, or an algorithm to evaluate that numerically when the CDF is not in explicit form. So here we have more curves. In black, we have the CDF, which is evaluated the p-norm function. This sample space is all real numbers here, although in the case of a standard normal, the probability that you get less than or equal to -3 is very small. You can't even see it on this slide, even though it technically goes off to -infinity and positive infinity out there. In the red, okay, so wait, question about CDF. How can we use the CDF to tell us what is the median of a standard normal distribution?
Equals 0.5?
Yes, and how did you arrive at that? Or CDF is what at 0.5?
Sorry?
I think you're right. Can you just explain it a little bit more?
Because when you're at 0.5, that means that you're exactly at half of all the things.
Probability?
Yeah, and then when you're at the middle point, then you're at the median.
Right. So median in the case of a continuous random variable defined as the point such that exactly half of the cumulative density is to the left and exactly half of the cumulative density is to the right. So we can start at 0.5, which is the value of the CDF, go over to the curve in black, and then down to the number on the horizontal axis to obtain the median, which in the case of a standard normal distribution is 0. Half the probability is on the negative numbers, half the probability, cumulative probability is on the positive numbers. Okay. So then in red, we have the curve that most people associate with the normal distribution. Now, what sort of is always frustrating to me is if you ask people, do you have a good understanding of probability? And they're like, yeah, I know the normal distribution, which is not all of probability, but they don't actually know the normal distribution. They don't know what's on the vertical axis of this. They just know it's a bell curve. but they don't know one of the axes. So do you really know, what the normal distribution is if you represent it this way if you don't know what a PDF is? Moreover, they don't know what is the equation that defines the red curve there. They just know it looks like a bell curve. So the equation is that. So even people who claim to know probability because they know the normal distribution don't really know the normal distribution in a lot of situations. But how can we use the PDF to tell us what is the mode of the standard normal distribution?
We just look to see the maximum value of the PDF.
So in the case of a continuous random variable, the mode is the place where the PDF is maximized, or equivalently, where the slope of the CDF is the highest. And in the case of a standard normal distribution, that is also going to coincidentally be 0. Again, the median and the mode are different concepts. They might happen to be the same number, and that is the case in the case of a standard normal, or normal distribution generally. Okay, green curve, we'll talk about more in a second. That is the function x multiplied by the PDF evaluated at x for a standard normal. And so that is going to be sometimes negative, sometimes positive, because x is sometimes negative, sometimes positive. And you can see, okay, if we just let x, the identity function, be our g of x function, then what is its expectation? That would be computed by seeing what's the area underneath the green curve. So that's sort of expectations graphically. What are they in terms of calculus? So if g of x is a function of some continuous random variable x from a continuous sample space, I said before, a probability density function is not a probability. Sometimes it's a little bit helpful to think the probability of a continuous random variable falling in a tiny, tiny, tiny interval. That can be represented by the PDF evaluated at x multiplied by dx, the sort of infinitesimally small number. And you can think of these dx as like the smallest number that you still have to keep track of. So like dx squared is so close to 0 that you can ignore it. And dx cubed is even closer to 0. So dx is like the smallest number that you still have to keep track of. And so with those concepts in mind, we can define the expectation of a continuous random variable using integrals. So the expectation of g of a continuous random variable is our g function multiplied by the PDF and integrated over the entire sample space of x. That definite integral, assuming you can evaluate it, but even if you can't evaluate it, that's the definition. So if you can put this in an explicit form like capital G, and then you evaluate G, capital G at the largest element of the sample space, and you subtract capital G evaluated at the smallest element of the sample space, that difference gives you the area under the curve defined as g of x times f of x. And that area is the expectation of g of x. So in taking expectations of continuous random variables, we use pretty much the same g functions. Instead of weighting them, doing a summation and weighting by a probability mass function, as in the discrete case, we're weighting by a probability density function and doing an integral rather than a summation. Integral is essentially adding area. Summation is adding points. But anyway, we often can't put these in explicit forms anyway, but that's the definition. Now, some of you may have used Mathematica in the past, and it is pretty good at evaluating integrals when that is possible, and to do it numerically when it's not, even though R and Stan can do numeric integrals as well. So Columbia has a program with Wolfram where Columbia students can download Mathematica for free. Although I'm not too high on Mathematica, it is useful for some things, and as long as it's free, you might as well take advantage of it. And so if you need to do an integral, you can do it, or you can do it with Wolfram Alpha sometimes. Anyway, so if g of x is the identity function, then we just say expectation of x has its usual symbol mu, even though it's defined by an integral. If g of x is equal to the function x minus mu quantity squared, the expectation of g is the variance of x. It's still the expectation of the square minus the square of the expectation. It's still given the Greek letter sigma squared. But anyway, it's the same g functions. It's just now we're weighting them by PDFs and integrating over the entire sample space, as opposed to what we did in the discrete case, weighting them by a probability mass function and summing them over the entire sample space. Entropy works a little bit differently in the continuous case, but I don't want to get into that right now. Does everybody have at least a conceptual understanding that expectation of a g function in the continuous case is going to be the area under some curve, and that curve is defined by g of x multiplied by f of x. Right. So in the case here, we have the g function, which is just the identity. So we have x times the standard normal PDF, and we have that curve in green. So how much area is under the green curve? 0, right? Because you can have negative area in the calculus sense, the area here that's in the negative numbers on the vertical axis. And we can see that this is a symmetric function, or what I think mathematicians would call an even function. But whatever, it's the mirror image of each other flipped around 0. So whatever negative area we have here is going to exactly offset the positive area that we have there. And so that's going to be equal to 0, provided these integrals converge, which they do in the case of a standard normal. But in general, this integral might not converge, in which we could say the expectation of the g function does not exist. Keep that in mind. We'll encounter some of those at some point. Question?
The meaning of the vertical axis for the expectation functions, like of the green function, is there a specific meaning of like the vertical axis or no?
No, it's just number. It has weird units, but whatever those weird units are, those are what you're accumulating area in. Yeah.
Is the XPDF here the second derivative of the PDF?
No.
No.
Not the second derivative. It's x times the PDF. So we're multiplying a function by the derivative of the CDF. But we're not differentiating the PDF again. Although you can differentiate the PDF in the case of a normal distribution and put it in explicit forms that involves Hermite polynomials, that's not really a thing. Other questions? Okay. So, like I said, we're not going to do a whole lot of this, but just to show you how it is done, usually many decades ago. So standard normal PDF only depends on the square of x. So if we wanted to calculate up its expectation, we would integrate x times little phi. We can split the integral at 0 and just make that the upper bound of the first integral and the lower bound of the second integral. But the fact that phi of x only depends on the square of x means that we can just multiply the first integral by -1, flip the limits of integration around, and we see we have the same function subtracted from each other. So provided those integrals converge, which they do in this case, that's going to offset to 0, which is just the calculus sort of version of what we saw in that green curve. A little bit more fun doing the variance of a standard normal distribution, which can be done in a couple of different ways. What I consider to be the easiest is to integrate this by substitution. So if we do a change of variables where we let y be half of x squared, then the relationship between x and y is given in blue there. It is the square root of 2 times y. And then the derivative, or dy dx, is going to be just x. So dy is equal to x times d of x. Then if we want to get the variance, we integrate x minus its mean, which we just found to be 0 squared, weighted by the PDF, phi of x. And so we can just plug in for phi there. Then substitute x for the square root 2y here. Substitute x squared over 2 for y there. And x dx gets absorbed somehow into this dy, and then we pull out the constants. Okay, so one tricky thing that I did there that I forgot to say. So this integral goes over the entire sample space, negative infinity to infinity. But again, because it only depends on the square of x, I can just integrate this from 0 to infinity and multiply by 2 to get that. So I've got a 2 on the outside, and then I pull my square root of 2 pi out. I'm left with this. So that is equal to y raised to the 3/2 times e to the negative y times dy. This integral here isn't elementary in general, but we can evaluate it in the case that the exponent we're dealing with here is 3/2, and that comes out to half the square root of pi, so that cancels with the 2 over square root of pi, which is equal to 1. So integrals of this form, this is known as the gamma function. It's another capital Greek letter. It's a very important function that's not elementary in general. It's a generalization of the factorial function, so we can evaluate it explicitly in the case that z is an integer. We can also evaluate it in the case that z is a half integer, like 3/2. But in general, it has to be evaluated numerically, and that's done by the gamma function in R. But in this case, 3/2, we can evaluate it explicitly, and so it cancels with everything, and we're left with the variance of 1. So a standard normal distribution has an expectation of 0 and a variance of 1. Those are technically theorems. Those aren't theorems I would ask you to prove on a homework, but that's how it's done. And it usually involves, like, if you can even evaluate these integrals explicitly at all, you know, tricks like integration by parts, change of variables, stuff like that.
Yeah, I was wondering, why do we do like y to the 3/2 minus 1 instead of like y to minus 1, or y to the power of 1/2? Is it because we need to force it into the form of gamma?
Yes.
Okay.
And you can a function explicitly for rational arguments. Whatever. Okay. So that's the standard normal distribution. Now, what actually makes this week the hardest is this slide. And I've been teaching this class for like 7 years now, and I've never been able to figure out why. But historically, you get this wrong. So if z is distributed standard normal, and x is a function of z, namely z multiplied by some constant sigma, and then you add another constant mu to it, what is the PDF of x? So we know, or we're given the PDF of z, and we're given a function that maps from z to x, and we want to figure out what the PDF of x is. So the first thing we have to do when figuring out problems like this is, okay, what do we know the distribution of? We know the distribution of z. So we need to be able to put this in terms of z. So if x is the function of z, specifically mu plus sigma times z, how can we write z as a function of x? Yes. So that is equal to x minus mu all divided by sigma. So far, not hard. All right. Step 2. Since this is a monotonic transformation between z and x, and we know that the probability, we're given the distribution of x, so we can think in terms of its given CDF, which is standard normal. So therefore, the probability that x is less than or equal to little x has to be the same as the probability of z being less than or equal to little z, considered to be a function of x. So here I have z, here I have it written as a function of x. Because this is a monotonic transformation, the CDF has to be the same number in both cases. So that's step 2. So we can think of that as capital phi evaluated at z of x. Now, if we want the PDF of x, how do we get that from the CDF? We take the derivative with respect to what? X. It's only 2 letters, but we want the PDF of x, and so we want to differentiate with respect to x. Okay, you might say, well, that's going to be really hard if we don't have the CDF of z in an explicit form. Not actually that hard, because all we have to do is use the chain rule one time. Derivative of capital phi of z of x with respect to x, we can differentiate phi with respect to z, and then multiply by the derivative of z with respect to x in order to get the derivative of phi with respect to x. Since we know the derivative of phi of z with respect to z is standard normal PDF, right? And then we multiply by the derivative of z with respect to x, which is, thank you, over sigma. Multiply those two things together, and we have the PDF of x, which in this case looks like the standard normal PDF. Instead of z, we've substituted what z is in terms of x, namely x minus mu divided by sigma. And then we have this 1 over sigma piece that I put down here in the denominator. Sigma is just a constant, doesn't involve x. So to summarize, the 3-step process to answering questions like this, when you're saying, here's the distribution of something, here's a transformation relating that random variable to another random variable, and you want to know what the PDF of the second random variable is. Step 1, you come up with the inverse function that maps the variable whose PDF you're seeking to the variable whose PDF, CDF, whatever is known. So come up with the inverse function. Explicitly or just imagine yourself evaluating or differentiating the CDF of the CDF that you know, written in terms of the variable whose distribution you're seeking. So we write the CDF in terms of x, so phi of z of x. We want to differentiate that with respect to x. So step 3 is to use the chain rule once. We know the derivative of the CDF with respect to the variable whose distribution is known is just going to be the PDF. We multiply by the derivative of the transformation from x to z. And the product of those things gives us the PDF of the random variable x. So you don't actually have to evaluate the CDF at all. You just have to take the PDF, write it in terms of x, and multiply by the derivative of the transformation from x to z. And that works in the case where the transformations are monotonic. Something similar works in the case where there might be like 2 solutions or something like this. Something similar-ish works in the case with multiple random variables, but we're going to start simple with this 3-step process. Okay? We will practice that even though you will get it wrong. All right. So then what's the expectation of x? Well, the expectation of x, since we know the expectation of z and we know what the transformation is, and we know that the expectation is like a linear operator, so the expectation of x simplifies to mu plus sigma times the expectation of z. So what's the expectation of z? 0. So we're left with mu. Expectation of x is mu. Variance of x. So since mu is the mean of x, so we have this expression here subtracted off mu. So that's just sigma times z, or really up there. If we subtract mu from that, we get sigma times z. We know expectation is the expectation of this function, so we're left with the expectation of sigma z quantity squared. We can pull the sigma squared out. We're left with the expectation of z squared, which is 1. So under a standard normal distribution, the expectation is 0, the variance is 1, and the expectation of z squared is related to the variance how?
Variance plus the squared expectation.
Yes. Variance is equal to the expectation of the square minus the square of the expectation. So if the variance of the standard normal distribution is 1 and the expectation is 0, 1 minus 0 squared is 1. So the expectation of z squared is also 1. Sigma squared times 1 is 1. So the variance of x is going to be sigma squared, which gives you some clue as to why we chose those symbols when doing this transformation. So this PDF of x is the PDF of the general normal distribution. And the general normal distribution has 2 parameters, mu and sigma. The standard normal is a special case of the general normal with mu equal to 0, sigma equal to 1. And so when we're creating these distributions, particularly in the case of continuous random variables, we usually start with a simple case and then do some transformation or limiting or something like that to get a more general function that involves more parameters that gives it more flexibility. We don't just have to fit normal distributions that have a mean of 0 and standard deviation of 1. We can fit, normal distributions involving any mean and finite standard deviation. All right? So that's an example of going from standard normal to general normal via transformation. And that transformation, scaling something up by a positive constant, shifting it over by some addition term, is a very common thing. And distributions that stay in the same distribution when you apply a transformation like this are known as the distributions in the location scale family. So they keep the same name, but they just change their parameters when you do a linear transformation like this to them. So normal distribution definitely falls in that category. All right. Another thing that is pretty directly analogous from the case of discrete random variables is bivariate random variables. So we can define a bivariate CDF of the continuous random variables x and y as the probability that capital X is less than or equal to little x, and simultaneously capital Y is less than or equal to little y. That is a bivariate CDF of the continuous random variables x and y, and in general it could depend on some parameters. So that's how we define the bivariate CDF. We define the bivariate PDF as the so-called total derivative of the CDF. So we first take the CDF, differentiate it with respect to x. That's going to give us another temporary function. Differentiate the temporary function with respect to y, and we arrive at the PDF of the bivariate distribution between x and y, and that generalizes fairly readily beyond 2 dimensions. So if you had like a 3-dimensional continuous random variable, you can take the derivative of the CDF with respect to the first thing, then take the derivative with respect to the second thing, then take the derivative of that with respect to the third thing. You'll have the PDF of the 3 random variables under consideration. And the PDF of the bivariate normal distribution, which involves 2 random variables x and y, so this is for the sample space, the real number plane. It's going to have 5 parameters: the mu expectation of x, the expectation of y, standard deviation of x, standard deviation of y, and rho for the correlation between x and y. And it can be written out like this if you just sort of look it up on Wikipedia, or if you look, if you do a rearrangement, you can see the following. So out here we have this term, which I can't highlight. Everything to the left of that, including that. That just looks like the marginal PDF, which happens to be normal, of the random variable x. So not standard normal, general normal, but it's just a univariate normal distribution in x. And it's multiplied by this thing here, which is very colorful, but merely a conditional normal distribution with new parameters. Mu is equal to the marginal expectation of y plus the ratio of the standard deviations between y and x times rho times the quantity x minus mu of x. So this is the conditional expectation of y given x. There's also a conditional standard deviation, which is equal to the marginal standard deviation of y multiplied by the square root of 1 minus rho squared, which is always going to be a real number because rho is constrained to be between -1 and 1. So if you do this rearrangement, you can see that the bivariate normal distribution for 2 random variables x and y defined in the real number plane can be written as a marginal PDF in x multiplied by a conditional PDF of y given x, because x appears in the conditional expectation for y. And so just like we have the multiplication rule in the discrete case, where we could take a marginal probability multiplied by a conditional probability and get a bivariate probability, as in probability of knocking down x1 pins on the first roll of a frame of bowling multiplied by the conditional probability of knocking down x2 pins on the second roll of the same frame of bowling, given that 10 minus x1 pins are available to be knocked down. So just the general multiplication rule in the discrete case. It's directly analogous in the case where the random variables are continuous. It's just we have to use PDFs rather than PMFs. So marginal PDF for x multiplied by conditional PDF for y given x. And in the case of a bivariate normal distribution, the marginal distribution of either of them, in particular x in this case, is univariate normal. And the conditional distribution is also univariate normal, but we've changed the marginal expectation by that second term there in red, and we changed the conditional standard deviation by scaling the marginal standard deviation down by a factor 1 minus rho squared. So the multiplication rule, Bayes' rule, those continue to hold when dealing with PDFs. It gets a little bit hairy, but this is actually the simplest form of conditioning when you have a bivariate normal distribution and you want to know like what's the conditional distribution of one given the other. So like in bowling, it was actually pretty easy to do the conditioning. With continuous random variables, it's often not so easy, even though the concept makes sense. But in terms of the algebra, I'm not going to go through it, but if you can go from here to here, you can see how conditioning works in the bivariate normal case. And the conditional distribution is univariate normal, as is the marginal distribution. So rather than dwelling on the algebra, we can show this graphically. So here, do not crash, do not crash, do not crash. Good, okay. Is the bivariate normal, general normal, density function. So where's my x at? Here we go. So we have x on the horizontal here. We have y on the other dimension. Maybe I need to make this a little smaller. There we go. Okay. And then on the vertical axis here, we have the joint density of those colored so that like purple or whatever is the highest density around the mode. It gets less as you go into blue and green and whatnot here. So with a bivariate distribution, we have to have 2 dimensions for the random variables, and then if we want to evaluate the PDF, that's going to be another dimension. And so I'm going to have extraordinarily limited ability to do this beyond 2 dimensions, dealing with a 2-dimensional screen here with the illusion of a 3rd dimension. But the idea generalizes to multivariate random variables more generally. So if we take this density function here for x and y under the bivariate normal, and we pretend we're like Google Earth or whatever, and we're looking straight down on it, like this. Okay. So now like our depth perception is messed up as to how tall this is, but if you just remember the colors, that corresponds to what has less density and more density. So now we're sort of looking in the XY plane straight down. Now, if we want to get the marginal distribution of y, how would we do that? Well, we might notice that this looks a lot like what we were looking at when we were looking at the joint probability table for bowling. It's literally a square in this case. Out here, the joint density is very small, so practically 0. But what's different is we don't have columns and rows. So we don't have squares, because this is not a discrete sample space. This is a continuous sample space. And so how do we, in the case of bowling, how did we get the marginal probability for the second roll irrespective of the first roll? Sum down the columns. Here I don't have columns, but I can integrate over x. Like that. Just mush the whole thing down. So integration is basically summing area rather than points. Okay? What does this thing look like when I integrate over x by mushing it all down to the bottom and put it in the margin? That can be visualized by taking this and turning it up like this, so that you are now looking directly across the y-axis. So this is, you're looking like this. And you're seeing the mountain there. So it looks like this. And you can see, well, this looks like a normal distribution if you can't see the depth on x. And that is what it would look like if you took that and integrated over x. It would look like just like you're looking just at the y part. So now y goes this way, right? and you can see it's a normal distribution. So the margin of a bivariate normal is a univariate normal for both x and y, or either x and y. Conditional distribution of x and y looks like this. So, you take like a particular x value, let's say, right here. So you have this thing, you want to look at both directions at once. Let's say I want a condition on x equal this, where my mouse is. It's like I'm taking a slice of this. So slicing across the plane right from here over to there like that. Just make a line through the plane. And then the line through the plane has to go over the hill a little bit, right around there. So it's like, that's what the conditional distribution of y given x would look like. And that is also going to be a normal distribution, albeit with a different expectation and a different standard deviation due to the conditioning on x. So conditioning on x changes the marginal expectation into a conditional expectation, changes the marginal standard deviation of y into a conditional standard deviation of y. But just like the margins of a bivariate normal are univariate normal, the conditional distributions of a bivariate normal are also univariate normal. Okay, so out of time for today. Keep working on the homework. Keep posting on CampusWire if you have questions. And if you want to stay around while we install our stand together and we can help each other, you can stay around for a little while. Otherwise, you can try it on your own tonight or tomorrow. And if you have problems, post on CampusWire. Question?
So in the template, you set the code chunk not to evaluate. Do you want us to do that all the way down?
Evaluate them.
Evaluate them, because some of them take some time, but it's okay. Just evaluate everything. Okay, because then we can pipe in text, and that makes it easier. Thank you.
Yeah, I just put eval equal false on that because it was not valid R code.
Gotcha. I didn't know if you want us to fill that in. Makes sense. Thank you.
Okay, done.